Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 35 in the series, Graphing Complex Numbers. So recall that the graph of a number is just a picture which shows that number and how it relates to others of its kind. Let's remember how we plot single real numbers, which are graphed on a number line. And this helps us visualize the rest of the numbers in the continuum of reals by which ones are greater and which ones are less than that number we've plotted. The continuum of points on the line sort of follows a natural order, one after the other, and that makes it great for dealing with things that also have an order, like numbers and the idea of being less than or greater than. Notice that we usually put the less than numbers on the left, the greater numbers on the right, and so if we see a number like A in this case, who appears next to a number B in this case, then we know that A being left of B means that A is less than B. Here we've plotted the two numbers A and B, and it sort of gives us some kind of reference to how one compares to the other. Here's a more concrete numerical example. If you want to graph 2 on the number line, we put a dot there, right? Sometimes we put a bunch of tick marks there, and we might throw some numbers beneath to kind of give some reference to what we're looking at, but the most important thing is that there's a 2, and the dot appears right above the 2. So now let's talk about complex numbers. With complex numbers, we have two real numbers. We have a real part, A, and we have an imaginary part, B. And order really matters in the sense that we can't change around who's A and who's B here. B is next to the I, A is not. So it really matters which is which. But wait a minute, we've already dealt with the problem of needing to graph pairs of numbers where order matters before. We looked at the plane, the xy plane, right? When we wanted to plot a point xy, we put the first number on the x-axis, the second number on the y-axis, and going up from the x and over from the y, we find the point of intersection. And this dot on the plane indicates the coordinate pair AB. So just like before, what we're going to do is we're going to use two number lines to graph the complex number. We'll make one for the real part and one for the imaginary part. Generally, the real part is assigned the horizontal axis and the imaginary part is assigned the vertical axis. And it's actually customary, even though the imaginary part is just B, we usually write BI here to remind us that these are indeed the imaginary numbers that lie, the pure imaginary numbers that lie on this vertical line. So if I wanted to plot the point A plus BI on what we call this, the complex plane, I would find where does A lie on the real axis, where does B lie on the imaginary axis, and going over from that, going up from that, we plot this point A plus BI. Here's a slightly more concrete example with some tick marks added. Here I've put tick marks across the real number line as they usually go, and notice I've written I, 2i, 3i, 4i, and so on, and negative I, negative 2i, negative 3i, negative 4i, and so on this vertical axis. So if I want to plot the point 3 plus 2i, I would first find the real part, 3. I would find the imaginary part, 2, 2i here, and going over from that, going up from that, we plot this point, and that represents the number 3 plus 2i. Now, I just want to take the opportunity to make a small historical digression. The term imaginary numbers. The great Carl Friedrich Gauss, who did much of this pioneering work, he hated that term. He didn't like complex numbers either. He thought that both of those were misinformed because there really isn't anything imaginary about these numbers that's different than what's imaginary about real numbers if we use the colloquial meaning. For example, real numbers you might think of as things you might see in the real physical world, but there are real physical things that correspond to complex numbers. And moreover, I've never seen any real numbers. I haven't ever even seen a 1. Not alone, not unaccompanied, just walking down the street with its shades on. I've never seen the number 1. I've seen 1 pen, I've seen 1 dog, but I've never seen 1 itself unaccompanied. It's another concept. It's imaginary in that colloquial turn of phrase, imaginary, right? It's a fiction. It's a fiction in the same way that the complex numbers are, but a very, very useful fiction. In fact, perhaps a true fiction. Now, just like the picture we just looked at, the imaginary numbers are really just to the side of the real number line. They lie above it and below it, but not on it. And so Gauss really wanted to call them lateral numbers. But the term imaginary is the name that's stuck. And so that's the name that we just have to work with. That's the colloquial way in mathematics of referring to these numbers, whether or not the usual day-to-day meanings of real and imaginary means something else. The mathematical terminology of real and imaginary means something very specific. And it's a good idea in mathematics to just get used to the idea that mathematicians name things, they're either really boring or really romantic. And they often have different meanings than the common usage of those terms. They have very specific mathematical meanings, and we just kind of have to get used to that abuse of terminology. Okay, digression over. Here's some more examples. Here's a very important number, which is 0. The complex number 0, 0 plus 0i, that's the origin. The number I itself is 0 plus I, if we wanted to write it in its general form, 0 plus 1i even. And that's along this vertical axis with the rest of the pure imaginary numbers. Here is the pure real numbers, right? Here's 4, lives right here. That's 4 plus 0i, no complex part, just the real part 4. And here's some other ones. Here's 2 plus 3i, you go to 2, you go up, you go to 3i, you go over, you put your point there. Here's another one. Here's negative 3 plus 2i. He lives right here. And here's negative 3 minus 2i, down by 2. He lives right here. So here's a number and its conjugate. Okay, that's enough for now. Let's do some critical notes. Copy down this box to let me know you watched this video. Complex numbers are graphed on a plane, the complex plane. Your real axis is your horizontal one. Your imaginary axis is your vertical one. And if you want to plot something like a plus bi, you find a on the horizontal, bi on the vertical, and you put a point where these two things meet. Here I've also plotted I and 1 for reference. Okay, so let's continue with a few patterns that we can notice about some of the arithmetic of complex numbers that we've looked at and how that relates to the complex plane. First of all, as we noted earlier, real numbers, they all lie along the horizontal. Pure imaginary numbers lie along the vertical axis. Also, what you probably noticed from the above picture, but is always true, complex conjugates are reflections over the horizontal axis. And that's a nice way to see, because nothing that's on the axis will move when you reflect it, that real numbers are their own complex conjugates. Like if you took a, for example, and reflected it over the x-axis or the real axis here, it doesn't go anywhere. It just stays right there. And just the same way, negating its imaginary part, well, the negative of 0 is 0, so it stays right here. On the other hand, a plus bi, well, the minus bi would reflect it down to a negative bi, and here would be our 2 points, one above and one below the real number a by the same amount. Likewise with bi and minus bi. You can see how these are reflections too. So another interesting geometric pattern has to do with sums of complex numbers. Let's take the complex number a plus bi and c plus di, and I've drawn them kind of askew from each other so we can really visualize this well. You can imagine an arrow sort of coming out from the origin and pointing at that dot, and an arrow coming out from the origin and pointing at this dot. And one of the ways that we could add arrows together is the same way that we add complex numbers together. I add their real parts and I add their imaginary parts, and that gets me a new number, a plus c plus b plus d, I. b plus d is now our imaginary part, a plus c is our real part. Well, a plus c just moves us up by c from a in this direction. Here di seems to be negative, so that would move us down from bi in this direction. And if we draw a new arrow, it has a relationship to these old arrows. It's like we moved this yellow arrow to the end. We say we add tip to tail of these arrows, and then it points to the new direction. And of course, addition is commutative, and so it doesn't matter if I went down this one first instead and up by the blue arrow, I still get to this dot. And that's something very useful. That's actually a pattern that you see in other kinds of math and in physics called vector addition. Now, don't worry about what vectors are. We're not covering that in this course. It's just interesting that the pattern of adding complex numbers reproduces that other pattern so nicely. And also, multiplication by a real number has something to do with multiplication and vectors and arrows as well. If we multiply a real number against a complex number, then it doesn't change the direction of this arrow. It just kind of changes how long it is, or maybe the direction in the sense of flipping it. So for example, here is z equal to 2 plus I. That's this blue arrow here. If I multiply by a real number like 2, then it just makes it twice as long, but it still points in the same direction. If we say put a minus sign in front of it or multiply by -1, it just flips the direction 180. It still points along this line, but now it's pointing down and to the left rather than up and to the right. So just an interesting geometric relationship about real number multiplication against a complex number. One more thing that I think is pretty important to know about for complex numbers and getting started with them is that we can sort of think of them as having a size or a magnitude or a length. Right? In the same way that we think about absolute value as being the distance from 0, I could think about the length of this arrow as being the distance from the origin. And how do you get that distance? Well, you could use the Pythagorean theorem. A squared plus b squared equals this distance squared. So if I take the square root of a squared plus b squared, I get this distance here. So this length of the arrow is what we get when we take the square root of the square of the real and imaginary parts. And remember, we looked at an example that produced this. If I multiply a number by its conjugate, I get a squared plus b squared. Okay, well, wait a minute, that's part of this. That's just missing the square root. And so you can actually use that to write this property. If I want to know the length of my complex number, or its size, so to speak, then if I just take its number and multiply by its conjugate, that's the square of its length. You could take the square root of this side and get its actual length. This so-called length of a complex number is often called its modulus, just a nice fun term for length of complex number. But it's nice to know that complex numbers also have a notion of size associated with them, just like distance from the real 0 on the number line gets the absolute value. We also use absolute values to indicate the size or the distance from 0 of a complex number. All right, that's enough of that. Let's talk about some praxis. Let's do some practical exercises here. Here I have 3 complex numbers for you, z and x. Z is I, w is 2 plus 3i, and x is -1 minus I. I want you to graph these points, and I also want you to graph the sum of z and w, the product of z and x, and the square of x, that is x times itself. Pause the video at this time and give it a shot. All right, let's see how you did. All right, here's the whole thing. Let's digest this picture. So we talk about z was I, that's this pure number here. We talk about w, that's 2 plus 3i. So we go to 2 up to 3i, that's our w. Here's x, -1 minus I, -1 minus I, so x is here. Now let's talk about the sum of z and w. That's I plus 2 plus 3i. We add the imaginaries together, that's 4i. And here is our z plus w. Notice that z was up straight from the origin by 1, and z plus w is up from w by 1. What is z times x? Okay, so we have to use the distributive property here. We distribute the I times -1 is minus I, and I times minus I is I minus I squared. This goes to -1, and so minus minus 1 is positive 1. We put the minus I at the end, and this is our new complex number 1 minus I. So here is z times x. Finally, let's look at x squared. So in order to multiply this complex number, 2 general complex numbers, we have to FOIL. -1 times -1 is 1. Minus I times -1 is positive I. Same thing with this outer term. And then minus I times minus I is positive I squared. But I squared is -1, so this is 1 minus 1, that's 0. There's no real part here. And then I plus I, that's 2i. So here I am at 2i. Okay, I wanted to give some supplemental notes. These are not necessary. They're just if you're interested in a little more information about the complex numbers. In the last supplemental notes, I looked at the roots of unity and how those related to, square roots, cube roots, fourth roots, and squares, cubes, and fourth powers, etc. It's very interesting that the graphs of those complex numbers that represent the roots of unity have this beautiful relationship. Notice that the second roots of unity are evenly spaced around the circle, and so are the cube roots of unity, and so are the fourth roots of unity. There's just 4 of them now, and so are the fifth roots. And when you evenly space points around a circle, what you get are the regular polygons. Well, this is kind of a two-gon, but here we have an equilateral triangle. Here I have a square. Here I have a regular pentagon, if I could actually draw it correctly. And so it's very kind of nice to tie together the most basic geometry, regular polygon geometry, with complex roots geometry, because they trace the same figures on the complex plane. By the way, if you wanted to know, here are the fifth roots of unity. They're actually quite difficult to write. There's a lot of radicals involved. If you want to take those in, that's excellent, but I've written them here just as a reference. So to summarize, the roots of unity are equally spaced on the unit circle, and so they make regular polygons with n sides. I wanted to make a quick note on a graphical interpretation of complex multiplication. The proof is a little bit beyond the scope of this course, but if your complex number has a modulus of abs-val of z, and it makes an angle of theta with the real axis. So here might be the picture of such a thing. And let's say w is another complex number with a length of abs-val w and phi as its angle. Then the product is going to have the following length: abs-val of z times abs-val of w. So the product of the two complex numbers, its length is just the product of their lengths. And the angle that it makes is going to be the sum of their angles. Here's an attempt to kind of draw that. Here's w, here's z, and if you go from w up by theta, you get this new angle, theta plus phi. And so we rotate, let's say, w by the angle that z had, or we could think of rotating z by the angle that w has. But either way, you get to this new red angle. And the length of that thing, here I've sort of drawn them both bigger than 1, so this thing gets longer. The length of that thing is just the product of their lengths. Actually, it's really not too hard to see that the length of zw is the length of z times the length of w. Just calculate both of those things. What zw, if z is a plus bi and w is c plus di, then zw is ac minus bd plus bc plus adi. If you want the length of that, you square both terms, and expanding and canceling the middle term that cancels, you just get ac squared plus bd squared plus bc squared plus ad squared. Now, what about the length of z plus the length of w? The length of z is a squared plus b squared. The length of w is c squared plus d squared. And if you expand that as well, just foiling, in both of these cases, we can prove this just by foiling, you get ac squared plus bd squared plus bc squared plus ad squared, which is exactly the same thing as the line above. So you can show this just by using the component definition of z and w. And that gives us a little glimpse about why complex multiplication might be useful, and indeed something that we should consider to be physical and existing in actual reality. Because rotation and dilation exist in reality. We can stretch or shrink things in reality, and we can rotate things in reality. And actually, complex numbers give us a way of talking about two-dimensional rotations and two-dimensional dilation and contraction with one single number. That's really useful, and in fact, something physical. If you have length 1 as a complex number and you lie on the unit circle, then these actually just correspond to pure rotations. So if you're thinking about, well, what good are complex numbers, a certain subset of them could represent all of your rotations that you might ever want to make of a two-dimensional thing. And of course, the real numbers, complex numbers that lie on the real axis, they just kind of scale things. They dilate, they make things bigger, or they contract, they make things smaller, while keeping all of the relationships similar. So no rotation, but dilation or contraction. And general complex numbers are a combination of these two things. That's all I'll say at this point in time. Thank you very much for your patience. Have a great day and good luck with your studies. I'll see you in the next one.